Hey, Sal Prep, this is Mr. Ellinger, and I'm just looking at the personal progress checks and just thinking about looking at them and going, I could see some people being kind of like, whoa, kind of overwhelmed by these. And so I just want to kind of do a video where I don't do the problems completely, but I just kind of break them down and make sure you see what's going on and that it's not as horrible as it might look when you first look at it. So here's question one. And so it's got a function, it's increasing on the interval 2 to 8, and let R3 be the value of the right Riemann sum. And if you graph this thing, it sure enough is increasing over 2 to 8, but it doesn't really matter for that, for us to get the idea of this. So we've got this function, and we know it's increasing from 2 to 8, right? And it's asking for, what's it asking for again? Whoop, there we go. It's asking for the right Riemann sum approximation. All right, so what is the right Riemann sum? And it's at 3 intervals. This thing's 6 wide. So if I'm going to break it up into 3 intervals, that means that it's going to be, sorry, those weren't even, at 4 and 6. And then I'm just making rectangles at each of those y values. So you use a calculator and you'll use the function and you'll figure out what the area of this thing is. If you draw a quick picture like this, it can really help orient what the heck you're doing. So that's why, like, once I see a picture, I go, oh, I know what the right Riemann sum is here. And it asks whether that's an underestimate or an overestimate for the true value of the area. Okay, and from the picture, you should be able to figure that out. Okay, that's about all I'm going to say on that one, because I think that's like enough for you to get started if you're stuck. Question 2. Whoa. Okay, so we're looking at 0 to pi over 2 of f of x dx, and they tell us what the exact value is. That's the correct number. It says if a midpoint Riemann sum with 2 intervals of equal length is used to approximate this. Okay, I'm looking at this. I don't know what this thing. I don't know what the actual. I don't know what the actual function. Like, I don't know exactly what this function looks like, but I can tell it's all positive between 0 and pi over 2. Starting 0 would be 0 because sine of 0 would be 0. And so I don't know what this one looks like, but again, it's going to be some kind of positive function. I have no idea what it looks like. Going from 0 to 2, 0 to 2 to 0 to pi over 2. That's right. And then it says a midpoint Riemann sum with 2 intervals of equal length is used to approximate what that true area is. Midpoint Riemann sum. What does that mean? That means, well, first it says 2 equal intervals. So we're going to approximate the area of the first one, and we're going to approximate the area of the second one. And so let's see, half of that'd be pi over 4, right? The way we're going to do it, though, to figure out like what y value should we use for the Riemann approximation, and it says the midpoint sum, so that would be halfway in the middle, and we want to use the y value there, and halfway in the middle, and we want to use the y value there. And you're going to use that to find the area. Remember, you'll be like making rectangles here, so like the base of the first one will be pi over 4, and the height will be, you'll have to figure out what the height is, and then same for the second rectangle. The base is pi over 4 and the height is whatever the height is. Cool. Next one. I gotta go a little bit faster, I think. But some of these I'm not gonna say anything about. Let g be a function of blah. Okay, calculator allowed. Awesome. Over 0 to 3. Okay, don't know what it looks like. I'll graph it later. At what value of x does g attain a relative maximum? So g is the area from 0 to x. So if you think about it, I could say a few things that we might see on this one. So like, imagine that it was always positive between 0 and 3. That means that this thing doesn't achieve a maximum until you get to the end, because the integral is always accumulating more. Like, it's like if you stop somewhere and say, ooh, that's the relative maximum of the integral, you say, no, keep going, you'll get more stuff, And so you'd want to go forever and ever and ever and get to the end, and make it as big as it possibly could be. Sorry, I just need to leave myself some space here. So, okay, so if that's not going on, then what else could be happening? Well, imagine what happens if we have a function where it goes like this. And this is before 3. Then we're going to be accumulating more and more and more stuff. And then at this point, we'll have accumulated up to a point, and we'll have some value for what that integral is. And if we keep going, then the area is actually going to start going down because now we've got negative accumulation that's kind of canceling it out. So we're looking for something like this. That would be a relative maximum in the middle. Now, you might be wondering, well, what does that have to do with relative maximum before? Remember what we said, the relative maximum first derivative test, you look for where f prime of x changes from positive to negative. And remember, our function is the integral. So our function is the integral from 0 to x of whatever the thing is. So the derivative of this is just, the derivative of this function is just x plugged into that function. And so it's just the y values right here. So where do the y values change from positive to negative? That's the idea on this one. So it's a tricky one when you look at it, but then it's not so bad once you take it back to derivatives. First derivative test. Next one, okay, and now they want a left Riemann sum, and so, but they're just going to give you points. So instead of having a function, you've got a table of values. So it's very similar to the earlier one. I'm going to skip that one. Move on. Okay, let's talk a little bit about sums. Which of the following limits is equal to that thing? Okay, so we got to think this thing through. And we could go back and we could look at the notes, but I'm going to just graph this and think about it. All right, what do we got? We got an area from 2 to 5, and we've got some function that I know is positive, right? What the function is. And we're going to find the area of this thing. And this is, the format that we looked at was we looked at the right Riemann sum as the best way to look at this. So what would be the right Riemann sum of this? Okay, so the first thing is we'd go over a certain amount for the width. And if you remember, the width, the change in x, is b minus a divided by n. So that's going to be 3 over n. Think about it. If you had n equal 3, so you had 3 intervals, then each one would be 1 unit wide, 3 over 3. If you had n equal to 6, you had 6 intervals, then it would be half a unit wide, each one of them. So that's all this numerator stands for, is a total width, and then you're dividing that total width up into n rectangles. Okay, so that's what the change in x is. And now what's the height of this thing? Well, the height of this thing, if I'm using a right Riemann sum, is going to be whatever the function value is right there, which would be 2, this would be 2 plus 3 over n. And then you plug that into the function. The next one would be 2 plus 2, 3 over n's. And so if you do a bunch of these things, whatever these widths are, then any given one, if I skip ahead, is going to be 2 plus I, 3 over n's. Whatever number it is. If I'm up to the 5th rectangle, then it's going to be 5, 3 over n's. All right, so you can go back, and you can see with the stuff here, you can see some differences. Notice how, I can't mark on this. I mean, I could, but it's going to be too much of a pain. So notice how some of these have 1 over n as the widths at the end, and some of them have 3 over n's. And then some of them have the function with just 3 over n, and they use k instead of I. That's totally fine, whatever. So 3 over ni, they just have that plugged in, but this has 2 plus 3k over n, or 3 I'm in my notation, it's I times 3 over n. I just think it's clearer that way. And that's plugged into the function. Take a look and figure out which one is the right one out of this. This is the kind of thing you need to be able to do with Riemann sums. On the next one, they're working backwards. They're saying, okay, suppose this was your sum, then what was the original problem? Well, one thing you can look at is you can look at this thing, and you know what the width of the rectangles are. So that means you know how wide the whole range is that we're finding the area of. Right? Notice how the function, they pretty much clearly show it's sine squared of x plus 3, and then sine squared of just with other stuff plugged in. Okay? Now check out this thing over here. So it's sine squared of 1 plus, and then this would be I times 4 over n in my notation. So I hope you're taking a look at that. And you're going, oh, okay, so it's having me start from 1 and then count over a certain number of 4 over n's. So what would that tell you about the bounds of the integral? That's the little hint there. Trying to think of any other little tidbits. I think that's it. I think those are the key factors. Again, you might have questions about it. You might not get them all right, but that's the kind of stuff that you're looking for here. You're looking at the width of the rectangles, and then you know this is 1 plus some number of those widths is what that part is. All right, where are we going? Ooh, 10:30. Got to move up. Right Riemann sum, same thing, except this one, it's not the actual area. It's just a right Riemann sum, so it's not as n goes to infinity, and that's the only difference between this. Otherwise, it's just like the problems from earlier, from like the other two. And I'll see if there's anything more I want to say. Derivative of the integral, fundamental theorem 2. Looks like a, can I scroll that down? There we go. H of x is the area under this curve. What is h prime of 3? Then take the derivative of this, think about fundamental theorem 2, and then plug in 3. I just don't think I have anything more to say about that one. I just want to make sure we're clear. Boom, boom, boom. Again, that looks like fundamental theorem 2 to me also. Yeah, this one looks kind of interesting. So remember, the critical points are where the derivative is 0 or undefined. They say it's differentiable, so you don't have to worry about about undefined. So where the derivative is 0. So it says the number of critical points for f in this interval. So that's where f prime of x equals 0. So you can take the derivative of this side, you can take the derivative of both sides of this, and find a formula, a very simple formula for what f prime of x is. And then you're looking for what are the most number of critical points and looking at positive to negative switches. It's an intermediate value theorem. You know, if you know a function is continuous and it's negative at one point and it's positive later, there must be a spot in between where it touched every single value, including 0. Hope that helps. And finally, number 12. I don't think I have anything to say about this one, but I'm just checking it out. Looks totally fine. I'm not going to say anything about that one. So anyway, so I just thought the sums, I thought giving you a little bit of context to help you see what to look for. And because the notation is slightly different in there, so I wanted to take a look at that. And then with those Riemann sum problems, man, they gave ridiculous functions. They don't tend to do that on the actual AP, and I think they're kind of stretching you in this. They tend to make things that are a little easier to plug in the calculator because they don't want plugging into the calculator to be the thing they're assessing. So so remember that these are personal progress checks to say, okay, what do I know, what don't I know, and don't think of them as a practice test in the same way. Okay, all right, that's it. Hope this helps if you had some major questions.